Hello everyone, my name is Amey Bhangale, and in this talk I'll be discussing approximability of satisfiable constraint satisfaction problems. And this is joint work with Subhash, Khot and Minzer. So let's first look at well-known CSPs before I formally define them. So in 3-SAT, we have n Boolean variables, and each constraint is the OR of 3 literals. In K and the constraint involves AND of K literals, and in 3-lin over a group, the variables take values from the group, and each constraint is a linear equation involving 3 variables as shown. So here A and B are group elements, and the goal in constraint satisfaction problems is to find a satisfying assignment. So next, let me define CSPs formally. So here we fix a K predicate P on sigma. The variables take values from the domain sigma, and each constraint is the predicate applied to a set of K variables. Okay. So in order to take this, make this problem interesting, for every predicate, we allow literals instead of just the variables for properly defined notion of literals. So here the goal is to find an assignment to the variables that satisfy as many constraints as possible. So more formally, for an instance phi and a value beta, the value of the instance on beta is the fraction of the constraints that are satisfied by beta. And the value of an instance is the maximum overall assignments beta, the value of the instance on beta. Now, since many CSPs are NP complete, in order to design better algorithms, we study approximation algorithms. An algorithm is called alpha approximation if it always outputs an assignment with value at least alpha times the optimum value. Now, for instance, for 3-SAT, if we pick a random assignment, then it is not hard to show that it satisfies 7 or 8 fraction of the clauses in expectation. And hence, this gives a 7 or 8 approximation algorithm for 3-SAT. Now, in this paper, we're interested in characterizing the approximation threshold for every CSP. Now, in other words, for a given values of C and S, if the instance is C satisfiable, then is there a polynomial time algorithm that finds an assignment with value at least S? So think of S as smaller than C. So we call this problem CS gap CSP problem. And we say that the gap problem is NP hard if the above is not possible, assuming P not equals to NP. So here let C is called the completeness parameter and S is called the soundness parameter. Now let's look at a few predicates for which tight results are known for some values of C. So for 3-SAT, Foster showed that the random assignment algorithm is tight. So even if the instance is fully satisfiable, it is NP hard to find an assignment with value at least 7 or 8. For 3-lin over a billion groups, if the instance is satisfiable, then one can indeed find a satisfying assignment in polynomial time, and this can be done using Gaussian elimination kind of technique. If, however, the value of the instance is less than 1, then Hostad showed that it is NP hard to do better than the random assignment. So here, for each variable, we independently assign a group element uniformly. So the same result as above holds for 3-lin over non-abelian groups. Now, when the instance of 3-lin over a non-abelian group is fully satisfiable, then unlike the abelian case, here it is NP hard to find a satisfying assignment. It is, however, possible to do better than the random assignment algorithm. And in the result with Khot, we showed that it is possible to achieve 1 over GG approximation. So where this set GG is the commutator subgroup of G. And the size of the commutator subgroup can be smaller than the size of the group for certain non-abelian groups. So that's why this algorithm is better than just picking the random assignment algorithm. Now, coming back to characterizing the threshold for every CSP, we have a huge success, and this is by the result of Raghavendra. So one can write a basic semi-definite programming relaxation for max CSP. And since this is a relaxation, the value of the STP is can be higher than the value of the instance. Now, Raghavendra showed that if there is an instance where the STP value is C and the integral value is S, also called a CS integrality gap instance, then the CS gap CSP problem is NP hard up to this factor of epsilon. And this is assuming the unique gains conjecture. Now, one drawback of this result is that it always loses perfect completeness. That is, this cannot be used to show NP hardness of one S-gap CSP problem, as the SGP value is at most 1, and we always lose epsilon in the completeness parameter. And this leads to the main question that we study in this paper. Can we find a characterization for satisfiable CSPs? That is, if the instance is fully satisfiable, can we find an assignment that satisfies at least S fraction of the constraints in polynomial time? And more formally, given a predicate P, what is the smallest S such that one S gap CSP problem for that predicate P is NP hard? First, it is highly non-trivial to solve the question or to decide if the smallest S for a given predicate is less than 1. And this is the famous dichotomy conjecture by Feder and Worthy, and which was independently resolved recently in a breakthrough results by Bulatov and Shuk. So they showed that for any predicate P, either it is solvable in polynomial time or it is NP hard. So given this, the next question is to find the optimum value of S for every predicate P such that one S gap CSP problem is NP hard. Now in this talk, I will focus on the most important component of the reductions for proving hardness of approximation, and that is this dictatorship test. So here we are given a function from sigma to the n to sigma. Sigma is some finite domain, and the function is called a dictator function if it always outputs a fixed coordinate from its input. Now, I won't formally define what I mean by far from dictator functions, but you can think of these functions as not defined fully by a small subset of variables. Now, in this test, we are allowed to query f at a few locations, and based on the values at these locations, decide if f is a dictator function or far from dictator functions. And if f is a dictator function, then we want the test to accept it with priority 1. And if f is far from dictator functions, then the test should accept it with small probability. Now, coming back to Raghavendra's result, for satisfiable or nearly satisfiable CSPs, let's first understand why we lose this epsilon in the completeness case. So here I'm formally defining the integrality gap instance. So if there is an instance of this CSP with predicate P, where the SGP value for that instance is C and the optimal integral solution is optical integral value is S, then it is called a CS gap instance for that predicate or for that CSP. Now, as stated earlier, it is enough to focus on dictatorship test to prove the previous result. And in this respect, Raghavendra showed how to convert one S integrality gap instance to a dictatorship test with completeness 1 minus epsilon and soundness S plus epsilon for any positive constant epsilon greater than 0. Now, for a given K predicate, if you want to use this dictatorship test to prove hardness results for a hardness result for that predicate, one technicality is that we want the test to query K locations and decide this accept or reject based on whether these K values satisfy the predicate or not. Now, leaving that aside for now, what we are interested in is to avoid this loss of epsilon in the completeness parameter. Now, we can view the K queries in the test as follows. First, fix a distribution mu on the set of satisfying assignments for P. Now we sample each column from mu independently. Then each row gives us one query location. And we query F on these K locations given by these rows. And we accept if it belongs to the predicates accepting assignments. Now, Raghavendra showed that the correct distribution mu is to take something called local distribution from the CSP solution of the 1S integrality gap instance for this max CSP. Basically, this distribution is always supported on the set of satisfying assignment, just because the SDP value is 1. In other words, since the SDP value is 1, the support of this distribution is always contained in the set of satisfying assignments for P. And that's why if F is any dictator function, then this will output just one column. And then by definition, each column is supported on P inverse 1. And hence the completeness of this test will be 1. Now, but then what is the reason behind losing epsilon in the completeness in Raghavendra's result? And for this, we need to look at the soundness analysis. So let's analyze the soundness of the test for this predicate P. And recall that we need to reject functions far from dictators with high probability. Now we can write down the acceptance probability as shown. So it's just querying its expectation over these queries and then checking whether these queries, the function values at those locations, they satisfy this predicate or not. Now we can break this into two parts, one involving only low degree parts of F and another involving high degree parts of F. Now the low degree part contributes S to the probability if F is far from dictator functions. And Raghavendra showed this by somehow using this low degree part to round the STP solution. And since we know that the optimum value is at most S, you cannot get anything better than S in this rounding. And that's why the contribution from the low degree part in this acceptance probability is at most S. Now this means that if we want to show that the acceptance probability of the test in the soundness is S or S plus epsilon, then we essentially need to show that the contribution from the high degree part is negligible in this expression. And in order to show this, Raghavendra used the following lemma by Mossel to control the high degree terms. So this lemma says that if the distribution mu is connected, then the expected product of these functions, which are balanced and bounded and high degree, this whole expectation is small. So this quantity, it goes to 0 as the degrees of this function they increase. And okay, so now in order to control high degree terms in the soundness analysis, here is what Raghavendra did. So instead of working with this distribution mu, which is coming from the STP, we can work with a distribution which is slight perturbation of this STP distribution. So in other words, we sample from this distribution mu, except that with probability epsilon, we sample it from another distribution eta. And this distribution eta will be uniform on all assignments, not just a set of accepting assignments. So it's uniform on sigma to the k. Now, this makes the distribution connected as given in this lemma. And hence we can we can say that the contribution from all the high degree terms is 0 or essentially 0. And what we are left with in the acceptance probability expression is just a low degree part. And that's why we can now claim that the soundness of this test is S plus epsilon. Now, since we added noise to each coordinate, this one, with probability epsilon, we sample it from outside the set of the accepting assignment for P, right? And hence, if F is a dictator function, then it can no longer pass the test with probability 1. So it can only pass the, so if, let's say if F is the ith dictator, then it can pass the test if for the ith coordinate we sample it from mu and not from eta. But with probability epsilon, we are sampling it from eta, and hence with probability roughly 1 minus epsilon, the ith dictator can only pass the test with probability 1 minus epsilon. And so the question that we try to answer in this paper is, can we relax this connectedness condition and still guarantee the conclusion of this lemma? And if we can do that, then we can get dictatorship tests for predicates without losing the completeness as compared to the STP value. Now, towards this, let's look at one condition such that if the predicates satisfy this condition, then the conclusion is false. Okay, and that will help us finding the right property for which the conclusion holds. So let's say a predicate has a linear embedding, if there exists an abelian group G and mappings alpha, beta, gamma that map this domain sigma to this group, such that first the mappings are non-trivial, at least one of the mappings is non-constant, and for every satisfying assignment ABC, if we look at the corresponding group elements, then they always add up to 0. And this is addition over this abelian group G, and 0 is the identity element from this group G. Now, if P has a linear embedding, then the statement of the above statement is clearly false. And here is a small example. So here you can take the domain to be 0 and 1, and G to be the parity function on M variables or N variables. Now, if N is large, then G is indeed a high degree function. And if mu is supported on odd parities from 0, 1 to the K, then it is not hard to see that the expectation is 1. So this expectation is 1 for these functions and this distribution mu. Okay, and this example can be generalized to other predicates that have a linear embedding. So the main lemma from our paper shows that essentially that is the only obstruction, at least for 3-array predicates. So what we show is that if a 3-array predicate does not satisfy any linear embedding, and if the predicate is semi-rich, which I will define next, then the conclusion holds. Then if we take this expectation and expected product of these 3 high degree functions, then this expectation is small. If the distribution mu is fully supported on P inverse 1 and the predicate P is not linearly embeddable and semi-rich. So let me define this condition semi-rich formally. So a predicate P is called semi-rich if for every A and B there exists a C in sigma such that ABC is a satisfying assignment. And similarly, for every A prime and C prime, there exists a B prime such that A prime, B prime, C prime is a satisfying assignment. So you can think of this semi-rich condition as the predicate being somewhat dense. And our lemma says that if the predicate is dense in this manner, and if the predicate is not linearly embeddable, then we can really control the high degree terms. So a few remarks. Now we can now convert this CS integrality gap instance to dictatorship test with completeness C and soundness S plus epsilon. And note that we do not lose anything in the completeness because of this theorem. So this is not quite true because we need some more technical conditions on the actual integrality gap instance. We want that every local distribution to be fully supported on P, because only then we can use this lemma to control the high degree term. But if the STP solution satisfies this condition, then we can convert this CS integrality gap instance to a test with completeness C and soundness S plus epsilon. Now, as stated earlier, this not linearly embeddable condition is a must. And in our work in progress, we also get rid of the semi-richness condition, and thereby proving the correct version of this lemma. This is the only condition. So if the predicate satisfies, if the predicate is not linearly embeddable, the 3-array predicate is not linearly embeddable, then this expectation is small. And one can use this lemma to get new hardness results, but this gets a bit tricky because now we can't really use unique games conjecture as a starting point, because we don't want to lose anything in the completeness, right? So, but one can use some stronger conjectures like rich 2-to-1 games conjecture, and if the predicate is good enough, then we can indeed convert this dictatorship test to a hardness result without losing anything in the completeness parameter, assuming the rich 2-to-1 games conjecture. Now, let me conclude my talk by stating the obvious generalization of our main analytical lemma to all k-array predicates. So here we can naturally define linear embeddability for k-array predicates. So I'll just say that in words. So a k-array predicate is linearly embeddable in an abelian group G if there exist k mappings from the domain sigma to G, such that for every accepting assignment, if you sum up the corresponding group elements from that is given by the mappings, then the sum is always 0, the identity element of the group. So if the predicate has no linear embedding, then the expected product of high degree functions is small. Recall that we can show this for 3-array predicates, but as of now, we don't know how to extend that to 4-array, 5-array, and higher array predicates. And we can lecture that this condition is enough for this conclusion to hold. Another interesting open question is to use this linear embeddability condition to design better approximation algorithms on satisfiable CSPs. That is, can we combine this Gaussian elimination technique and the SDP rounding technique to get better approximation algorithms for satisfiable CSPs? So if the CSP instance is satisfiable, and if the predicate satisfies some linear embeddability condition, then can we use this to design better approximation algorithm or do some sort of Gaussian elimination to get better approximation algorithm on such instances? Okay, that's all, and thank you for listening.